we're going to look at representing 2D transformations in terms of matrices here. The first matrix we're going to look at and see what it does to coordinates and therefore shapes on a graph is the matrix with constants K1 and K2 along the leading diagonal. So the way we check what this does to our graph that we have, or drawing on a coordinate, a Cartesian coordinate system, so we might have some shape right on the XY coordinate plane, and every point on here will have some XY. Okay, so some X coordinate here and a Y coordinate there. Alright, so each point on this triangle here can be represented as a vector XY, okay, for a particular value XY. So we're going to multiply this matrix by XY, and this yields K1X, K2Y. So a matrix of this form gives a stretch of K1 in the X direction and a stretch of K2 in the Y direction. So that's a pretty simple one. Of course, if K1 is 1 or K2 is 1, then the X and Y just stay as they are. On to the next one we're going to do. We're going to look at some reflections. So if you take -1, this is essentially taking K1 as our -1, and we multiply by XY. We get -X and Y, so this is a reflection in the Y-axis, okay, because the Y points stay the same, the X points move, so this point would go over here, and this point would go somewhere around here, and this point would come to here. Okay, so we get like a reflection in the X-axis. And similarly, if you have 1, 0, 0, -1, and you multiply this by X and Y, you get X minus Y, and that's a reflection in the X-axis. Okay, turns out these are actually special cases of another type of reflection matrix we can get. In general, the matrix cos 2 theta, sine 2 theta, sine 2 theta minus cos 2 theta, that gives a reflection in the line y is equal to x tan theta. Okay, so if you want to find the reflection matrix for a particular line, you have to solve this equation here. So the line will have to go through the origin. As you can see, there's no constant term here. So you essentially have an equation of the form y equals mx. So you want to solve for m is equal to tan theta and solve for theta. and then you can plug that into this matrix, and that will give you your reflection matrix. Okay. A similar matrix is a rotation matrix. So if we multiply by cos theta minus sine theta, sine theta, and cos theta, we get a rotation theta degrees anti-clockwise. Alright, and I'm not going to go through exactly why these are true. So, kind of intuitive, especially if you look at the cases for particular values. Like if you consider particular coordinates of x and y, like 1, 0, and 0, 1. Even do -1 and for each of these, then you can start to see why this is true. And I encourage you to look at that if you want to look further into the subject, but it's not really required for the syllabus. You just need to be able to use these matrices, so I'll just leave it there for now. The only other thing is, how do we combine these together? So as an example, you might want to see the effects of might want to find the matrix which represents the transformation of a 90-degree rotation and anti-clockwise, followed by a scaling of 2 in the x direction. So what you have to do is, so you have a point xy, and you want to move the point 90 degrees anti-clockwise. So we first apply our rotation matrix, so that would be cos 90 minus sine 90 sine 90 and cos 90. Of course, cos 90 is 0 and sine 90 is 1, but we'll factor that in later. And then we have to multiply by, our matrix is going to scale in the x direction by 2, so we take k1 as 2, 0, 0, and y staying the same, so we just use 1 here. And this is equal, just simplifying the rotation matrix, so as we say, cos 90 is 0, minus 1, 1, 0, multiplied by xy, and this is equal to, so we go across the rows, down the columns, and we're going to get a 2 by 2 matrix in return, as we'd expect. So we get 2 times 0 plus 0 times 1, so that's 0. Then we get 2 times minus 1 plus 0 times 0, so that's minus 2 here. Then we get 0 times 0 plus 1 times 1, so that's 1 here. Then we get 0 times minus 1 plus 1 times 0. Now we can multiply this in. We get 0 times x plus minus 2 times y, so that's minus 2y. And we get 1 times x plus 0 times y. So you can see, by rotating the whatever graph we have, so it might look, could be anything, something like this. By rotating this, terrible drawing, 90 degrees, and then scaling it in the x direction by 2, our x coordinate, any x coordinate, so say this point has coordinate x, well, that goes to minus 2y. Okay, so we have our y here, corresponding y, we multiply that by 2, and go here, So our x coordinate becomes like over here, minus 2y, and y just goes to x, so for this value y here just becomes x, so it might go here, okay? Anyway, so in general that's a rule now. Now you have by using this matrix representation, you can now take any point and you know what to do with it to get it to a new point after the transformation. Right, that's all we're going to do for 2D transformations. We tried to just get the idea in here. We're going to move on to 3D ones in the next video and just give the rules for you to remember. Essentially, maybe put a couple more examples in. If you do find this difficult, then please let me know in the comments. I'll try and make a more in-depth video of why this is the case and all that stuff, because it can be a little bit weird to get your head around. But it's certainly one use of matrices, which we introduced in the last video, that's very important to remember. If you didn't see that last video on matrices, then I'm sure this video was very confusing unless you've studied matrices before, so be sure to check that out, and I hope to see you in the next one.